If I was to take that as a technical question, that question could be translated to please define infinity. So, you know, many have tried. I love Cantor's, I think, the best. Cantor is probably one of the best mathematicians that in history, and he's the one that proposed, did a really good job at defining the possibility that there would be an infinite amount of infinities. And so if I was to like describe singularity in a few words, that would be my probably go-to description, an infinite amount of infinities in a point. And what does that mean, an infinite amount of infinities? Well, it means that so to Cantor was not complete. The view was not complete. To most people, if you say an infinite amount of infinities, the tendency is to think that those are conflicting statements. If you have an infinity, how can there be an infinite amount of infinities in there, because you have an infinity already? In the context of a fractal, it starts to make sense. And, you know, eventually I'll find the time to complete Cantor's theorem on infinite amount of infinities with the feedback mechanism and the structure of fractal systems. Because if you're trying to visualize what an infinite amount of infinities are, you can do that in the context of a fractal structure. Because what you're saying, basically, is that infinities can be defined at any scale, meaning that you have scale relationships in which any scale you start from, you will find an infinite amount of smaller scales in that boundary condition. And each one of these scales that you're finding, right, in each one of these subdivision of this pixelation that you're finding into the one scale, you will find, you know, infinite amount of smaller pixelation in that scale as well, and so on and so on and so on to infinity. So you have an infinite amount of infinities, meaning each scale being an infinity itself, and that would be described as a singularity. So what is a singularity? Singularity is literally singular, meaning it is everything you see. Every point in space is a singularity, because every point in space is a little Planck oscillator, which is mathematically a black hole. And is the Planck scale the last scale, which would end the infinite amount of infinities? No, I don't believe so. I think that there's, you know, the Planck scale is most likely made of smaller infinities that are, you know, making up the pixelation of the Planck, except that these exceed the speed of light in their frequency, so in their wavelength, so it's not available for us to access. For the pixel of our universe, the Planck length becomes the bottom the fundamental pixel for our actually it's twice the Planck length, and for a reason that has to do with relativity, which makes up the first pixel. It is a black hole of twice the Planck length, and it has 64 Planck length oscillator in it that pixelated, and it has 64 on the surface, and it's the only black hole in which there's the same amount of information on the surface as in the volume. So it's the first one, and it's the most stable one. It's the one. It's extremely stable because it has 100% zero entropy across the event horizon, since there's as much information on the surface as on the inside. All the information can be exchanged. So all this, it's a difficult question to define singularity. Now, I hope this helped. I didn't give you the standard definition of singularity. So in the standard definition of singularity, you have two things. You have a mathematical singularity, which is not a real singularity. For instance, you have a mathematical singularity at the event horizon of a black hole. That is, viewed from the external perspective, a singularity forms at the event horizon of a black hole. If you look at the particle falling into the black hole, it would become frozen to infinity at the surface, because it, the dilation of time at the speed of light at the surface of the black hole would go to infinity, and you would not see what's going on with that particle anymore. But that's the fake. That's not a true singularity, because it, is based on your frame of reference. It's not a proper frame of reference. And when I say proper frame of reference, I mean it in technical language, which means the proper frame is actually the frame of reference of the particle falling through the singularity, or towards the singularity at the center of the black hole, and that one is a real one. But the particle passing the event horizon would not feel anything different when it passed the event horizon. It would just continue to accelerate towards singularity at the center of the black hole. And that is the standard description of singularity, is thus at the point at the center of a black hole, for instance, in physics, where you have infinite amount of mass, like space-time is curved towards infinity. And so you can imagine that the center of a black hole then is like a Planck scale. At the Planck scale becomes what I was talking about, which is the pixelation of space-time. And so what I'm saying to you is that, unlike the standard model, I realized that space-time is not just curved to singularity in the middle of a black hole. It's curved to singularity in every point in space, because it's all Plancks, which are mini black holes. They're like very, very teeny black holes. So they all are singularities everywhere in space. And then the singularities have bulk rotation, where they all rotate together in a certain region. And that makes larger black holes that we see in the cosmological world. Or as subatomic particles, like a proton, being a larger black hole than a Planck, and so on. And so now you have singularities in scale. The boundary of the singularity can be found in infinite amount of scales for the bulk rotation of the field itself. And so you have an infinite amount of infinities.